everyone, welcome to the session. So now in this video, I'm very excited to share with you all that we are starting our very first project in this machine learning, complete course. I hope that before coming to this video, you already have, completely understood the concept of linear regression. We have talked about a lot of mathematical intuition behind the same. Afterwards, we have seen a lot of, methods that how we can improvise our model evaluation techniques that we have in linear regression. What are the different sort of algorithms that we have with respect to the supervised machine learning algorithm, what regression problem is actually trying to solve. Everything we already have covered up, right? Now, as I told you in the very start of the course itself, that for every algorithm, the first important thing is to understand the mathematical intuition, and the second important thing is to understand the implementation for the same. So what we will do in the upcoming videos, we will try to complete our pipeline of understanding this particular algorithm, where we will start by understanding the data, where we will take a house price prediction data set. I'll try to show you everything from a very scratch, step by step. In every video you will see that there will be separate steps which we have in a pipeline that we will follow up. In the very first video, you will observe that we will be talking about the complete understanding of the data, where we will observe that from where I am picking up the data set, what that data set is all about, what are the features that we have in that data. Afterwards, we will talk about how we will be able to create a complete pipeline of the data, where for every record, how I will be able to attach the corresponding price. Yes, we need to do the preparation for that as well. In the third step, you will observe that I will be talking about the EDA step, exploratory data analysis, where we will try to filter out the garbage values, or in a way noisy data points or outliers that we have in a given data. And we'll try to deal with the null values if we have. We'll try to see that how we can, check the outliers by plotting the box plots. We will try to talk about pair plot. There are a lot many things that we will discuss in that session. After that, in the next upcoming session, in the fourth part of the video of the project, you will observe that we will be talking about the model training, where we will be applying an actual linear regression algorithm, and you will observe that logically understanding the mathematical intuition might seems to be complicated, but doing the implementation is very, very easy as comparable to that. That's why I always say that getting the results, doing the implementation is not difficult in machine learning, because we can directly fetch from sklearn the model part and do the implementation. But understanding that mathematical idea is pretty much important for you all as a beginner, right? Then the next important step, once we will be able to train the model, the fifth step is model evaluation, where we will see that what are the metrics that we have to evaluate that how that model is behaving. In the next important step, we will see that how the model is predicting. Obviously, we will try to see on the test data what are the predictions of getting that house price, whether it would be reasonable or not. In the next part, I'll try to show you that, okay, once we will be able to train the model, once we will be able to get a better results also, better predictions also, it's very, very important to save that model and how we can save that. And after that, the complete idea, a complete wrap up of the complete project I'll try to show you. So this is the complete idea of the upcoming part of the videos. I hope that you are excited with me. Please take a note that I will do all the implementation in Google Colab. But by saying that, we have various platforms to do the implementation. You have Google Colab, you have Jupyter Notebook, you have, Kaggle is also there, where you can go and check it out, how we can do the implementation. I'll show in one of the video the complete demonstration of these platforms which I'm talking about here. But yes, in the upcoming videos, you will observe that we are following all the code part in the Google Colab. It's a free based platform. Just you have to search on the web Google Colab and you will be able to get a new file. And you can also do the implementation with me. That would be a good idea to go ahead with the videos, so that you will also able to observe that whether you're getting the similar results which I'm getting or not. Okay. So with this, let's start this journey. I'll see you all very soon in the upcoming video, where now we will try to understand the data very first sight. Okay. Hello everyone. Welcome to the session. So now in this video, we will be starting our very first part, where we will try to understand the data. Okay. So the very first thing is that we need to install the required packages, which are really required to do the complete step of understanding the data. Now, because we are doing it in Google Colab, there is no specific need to do the manual installation. Everything is by default installed in this platform. Okay? But at any point of time, if let's say you are doing in your local system, so you have to manually install the packages required first. For that, I'm writing a command which you have to use. So the very first step is to install all the required packages or the libraries that we need. For that, the command is pip install. For example, let's say we are using NumPy. So you need to install it. Okay? In the upcoming sessions, I'll try to talk about the complete end-to-end pipeline in a Visual Studio where we will try to create a separate requirements.txt file where usually we used to write these libraries, and then there is one command pip install requirements.txt which we usually write, so that every particular library will be installed in one go rather than doing it one by one. But as of now, because it's the very first project that we are covering up in this particular project module, machine learning module, so take it very easy and we will try to do it in the Google Colab itself. So as of now, just consider that you have to do it for whatever libraries we required. Okay, for example, NumPy, Pandas, Matplotlib, Seaborn, and so on. Now the second important step, obviously we are skipping this step because we are doing it in a collab. The second important step is to import all the required libraries. So we need to import that. Perfect. So let's import this. So what we will do is we will say import pandas as PD, import NumPy as NP. Then we need import Seaborn as SNS. Then we need import matplotlib.pyplot as PLT. And in this way, we will be able to import all the required libraries. In the second step, what we will do is, usually what happened is, in the upcoming sessions, obviously we will take some dataset outside the, real time or from Kaggle, from various different platforms. But as of now, again, because we are starting, in the sklearn itself, we have by default lot many datasets to analyze to perform the task. So we are taking the data of this house price prediction from there itself. So we need to load the dataset. Okay? And the dataset that we are using is a California housing. So I'll directly load that data of a California housing. So what I will do is I will say from sklearn.dataset, as I told you, from there itself a lot many datasets are available. And from that, what dataset we need to import? We need to import fetch underscore California underscore housing, right? Now what we will do, we will say housing is equals to fetch underscore California underscore housing. So what we will be able to get is a complete set of data available for a California housing. Let's try to see this type of data, type of this housing data that we have. You will observe that this belongs to a sklearn.bunch kind of a data set. It's a dictionary, similar to dictionary based data, but not exactly the same. It's a data set which contains key value pairs itself with a metadata available for a given data. So if I just try to show you this data set rather than talking about a lot, here if we will be able to see, we will be having a key as data, and then we will be having a set of data points. Similarly, we have target, which is obviously a house price value. Similarly, we will be having a frame, target names, feature names, and so on. Similarly, we have description, which indicates a description of each and every attribute that we have in a given data. So if, let's say I want to show you the description value of each and every data available in this housing data set, so we can clearly see that here if you will be able to observe, we will be having 20,640 number of instances. It means the size of the data is also not that small. It's a very big data, not very big, but yeah, moderate size data is there. where you will be able to see 8 numeric values are there, predictive attributes are there, and the target value is there. So here if you will be able to see each and every variable or the feature name that we have in a given data set, the complete explanation is given to us. For example, med-inc. Obviously, via this variable, we will not able to get an idea what this variable indicates. So this definition is given that it's a median income available in a block group. Similarly, house age, it's a median house age in a block group. Average rooms, average number of rooms per household. Average bedrooms, average number of bedrooms per household. Population, block group population is available. Average occupation, average number of household members. Latitude, block group latitude. Longitude, block group longitude. So it means that blockwise the feature values of income, house age, number of rooms, number of bedrooms, population, and so on, features are available to us, and on the basis of that, what we want is finally we want to predict the price of the house. That's the real target that we want to achieve. So here if you will be able to see, if we will say print housing dot feature underscore names, so we can print that list of names, that feature values that we have in a given data set. Similarly, if let's say we want to see what are the what is the target value maybe which is available here, so you can clearly check that. You can say housing dot target, and here you will be able to see a list of all the given records house prices, right? 20,000 something records are there, right? So for every particular record, what is the house price available, that is provided to us. Okay, so similarly, if let's say I want to see the data, so what I can do, I can say housing dot data. It's a 2D kind of an array which is available. So again here if you will be able to see, data is available where for every attribute what is the value being available, it is there. So in this way we will be able to see the complete I would say data set, the description of a data set. I hope you will be able to understand this data, and you will be also able to understand the problem statement pretty well, that we will be having the attributes or the features correspond to every feature. We will be having a target number, which is you can say price of that particular house depending upon the house age, number of bedrooms, number of what are the values that we have, right? We have studied number of rooms per household, house age, income, and so on, right? So in the upcoming session, what we will do now is, in the next important step in the pipeline is that how we can prepare the data. That is the next important step. For the preparation of the data, as you can see that as of now, this is a sklearn bunch kind of a data type that we have. What we have to do is, first of all, we need to convert this data into data frame so that we can apply operations on top of that. We can do a EDA task on top of that, right? Exploratory data analysis. After that, we can do a model training on top of that. So step by step, in every video, I will try to explain each and every step in a great detail. So please stay tuned. I hope that until so far, you will be able to get my point, whatever I want to deliver it here. With this, let's end today's video. I'll see you all in the upcoming session, where now we will talk about the data preparation part, where I'll show you how we can convert, first of all, this data into data frame, and then how we can perform the further task on top of that. Hello everyone, welcome to the session. So now in this video, let's start doing the preparation of the data. I hope that before coming to this video, you already have watched my previous video where we have already understood our data and what attributes that we have in our complete data set, how many number of records we have, what is the meaning of each and every attribute name that we have. All these things we have covered up, right? So now, and in the very first moment, what we will do is, as you can see that the housing data that we have is not of a type of a data frame. So what we will do is, we will try to convert it into data frame so that we can do on top of that a lot many number of tasks, okay? So I hope that you are already aware about this command that we have in pandas, pd.dataframe, which is basically used to convert the data that we have into a data frame. So now what we have as an original data is housing.data, right? Which is the parameter that we have. In the last video, I have shown you also. And what is the columns that we have? So columns are there in the housing.feature names, right? In the last video, I have shown you also these things. by printing the values, right? So what I can do is I can print the feature names here. Now, let me do one thing. Let's run this. Let's see the type of this data set. What does this type looks like? The type of this data set. So here, if you will be able to observe, now we are good to go, because you can clearly see that the type of this data is a data frame, which is what we really want. And now I think it's the right time we can do a lot more operations on top of that to analyze the data. So here, if you will be able to see, in order to get the list of the topmost 5 records that we have, we do have a function or method called as a head. So basically what it usually do is it will try to take the top 5 records that we have and will try to bring it up in the form of a data frame. So here now you can clearly see 0, 1, 2, 3, 4 is obviously an index number. And here we will be having med inc, house age, average rooms, average bedroom, population, average latitude, longitude. Every meaning I already have explained in the last video in the description part. You can go and check it out. So here, if you will be able to see, this is the complete set of records. For the top 5 records, we can clearly see. Similarly, if you want to see the last 5 records, we have a method called as tail. This, if you will run, you will be able to get the last 5 records. So if you remember, we will be having 20,640 number of records. So last 5 index number that we have, and corresponding to every record, we will be having the values of the feature names that we have, right? I hope everyone can clearly see on my screen. Perfect. Now, moving ahead, what is the final outcome we want to achieve, right? Obviously, we want in our data frame itself another column, which is the last column, as a target value, which is the price of a house. And that is available in my housing target column, right? If you will be able to see housing.target, there the price is available, right? So what I will do is I'll try to add that price column, new column in the data frame of data set. So this is the price one. And what I will do is I will try to say from where I am trying to fetch, it will be housing.target, if I'm not wrong, right? So here, if you will be able to see, once you will run this, if we will again check it out, the topmost 5 number of records, we will be able to see that, right? So now our data is ready, right? For every record, I will be having 1, 2, 3, 4, 5, 6, 7, 8 attributes or the features that we have. And final outcome, final target value is the price, which is given, right? So now, if I just want to see the info of this particular data set that we have a function called as info, with the help of which we will be able to get the information of each and every variable feature that we have. So we will be having known null values. It means that the missing value is not available, as I can see from this information. Also, we can write a command to check the missing values. I'll let you know. Here we can see that the data type of this particular attribute is float64, right? After that, let's try to see the further description, statistical description of this data. So how basically we can check it out? We can just say data set dot describe. This will give us the description of a complete set of data points that we have. So you can see that the count is same. It means there is no null values. Mean is there, standard deviation is there, minimum value available in the complete, medding, house age, complete feature values, feature names that we have. What is the 25 percentile? What is the median value? What is the 75 percentile? What is the maximum value? So this is how for every particular columns that we have, we can easily able to calculate, and we will be able to get that values. You can clearly see that there are people who might not be having an idea about how basically mean, standard deviation, median will be calculated, the percentile 25, 50 or 75. These things are statistical concepts, and it is very important for you all to know the bits and tricks about the stats concepts as well, because you won't be able to get the clear-cut idea about the core concepts of machine learning if you're not good with the statistical portion. So I really request you all to have that idea pretty well. By saying that, it's not just the formulas which you will be aware of, but also the inference about those formulas, that what actually you want to convey from those variances, from those standard deviation, from those mean, median, right? It's very, very important. Now, let's move ahead. After this description, let's see if, let's say, I want to check the null values. Although we have checked it out, but what is the command to check it out? You can say dataset dot is null. Now this is null is a Boolean function. If I'll just run this simply, what you will be able to observe is it is giving me the answer as either true or false, which indicates that if the null value is there, missing value is there, it will say it as a true, otherwise it will say it as a false. So here what we are doing is, we want to do the summation of this to check it out, that for every particular index or the features that we have, is there any null values available or not? So here we will be having 8 attributes, right? So what I want is, for every attribute, how many number of null values are available. So what I will do is, I'll run this, and you will be able to clearly see that whatever assumptions we have made and whatever inference we have made by seeing the count value in the description part and the info value in the dataset part, it makes sense. It makes sense because the known null values are not there, missing values are not there. If they are available, in that case you have to do the data imputation, means you have to fill that missing value with some number. Now that number can be mean, it can be median, it can be mode, it can be, you can apply some algorithm to predict what can be the optimal value. There are several ways to do the data imputation. Maybe in the upcoming projects, when we will take further different kind of a data set, there you will be able to see that, okay, there is a missing value, and then I'll show you that how and what are the techniques of data imputation that we have, and how we will be able to check that which is the best suitable value with respect to that particular feature that is available to us, right? But as of now, that issue is not there. So let's not focus on that point. And in the upcoming video now, I think it's the right time that we should move ahead to the next important step, which is the EDA. The full form of EDA is Exploratory Data Analysis, that we will try to understand now. Okay? Exploratory Data Analysis. Perfect. So in the next upcoming video, what I will do is, I'll try to do whatever steps are required to analyze the data, to get the better insights of the data, to filter out the content which is actually required to get the desirable results, to get the desirable predictions of the house, right? So we'll try to do step by step each and everything, but I think whatever things just now we have done in order to prepare our data in a way that we will be having now data frame, where we will be having proper feature names correspond to every record, every feature. We will be having a target value, which is a price value, right? I think that part is pretty much clear to everyone. So if you still have any doubt in terms of that part, please do let me know. Please do reach out to me and ask me the concerns if you have. Hello everyone, welcome to the session. So now in this video, we will be starting doing the EDA part. I hope that before coming to this video, you already have watched my previous 2 videos where basically we have understood the data which we are dealing with. In the second portion, we have already prepared our data in a way that we will be having for every record a corresponding price value, which is the target value that we have, right? We have seen also in the last video that there is no as such null values which are there in our given data set. That's why there is no as such need of doing a data imputation, right? So now let's get started to see the statistical analysis of this particular data set. We are doing EDA. I hope that you already have a clear-cut idea about EDA portion. Its full form is Exploratory Data Analysis. As the name itself suggests, that here we want to analyze the data in a way that we want to filter out the quality content out of the given data. Obviously, the higher quality data or content that we have, you will be able to understand that the better accurate predictions we will be able to get, right? So in the complete life cycle of any machine learning or deep learning or data science based projects, If let's say someone will ask you that where the developers will spend most of their time in the complete life cycle, no, it's not in model training. No, it's not in model deployment. The major time that they spend in EDA. Why? Because as I told you, the better quality of data we will be able to get, the better accurate predictions we will be able to perform afterwards, right? So in today's session also, we will spend most of our time in doing the analysis of the data. You will try to observe what are the steps required to perform in EDA. There are lot many steps depending upon what kind of data we are dealing with. But today I'll try to show you few of them, and we'll try to get the insights from that data, right? So until so far, if you will be able to observe, in the very first part, we have already understood the data, right? We have spent our time in terms of understanding the data values or data points that we have. In the second life cycle of complete project, we have talked about data preparation. Data preparation. After that, now we are talking about exploratory data analysis. Exploratory data analysis. And as I told you, this is one of the most important step out of all the steps that we will cover up. Okay? The very first thing that we will do in this EDA part is to find out the correlation coefficient value. Now, what is the meaning of correlation coefficient? Let's try to understand. In statistical terms, how we basically usually find out this correlation coefficient, you can go and refer the stats videos for that. But I'll try to give you the inference behind finding this correlation coefficient. First of all, if you will be able to observe, the value of this correlation coefficient will lie between -1 to +1. What does that indicate? This indicates that either the two variables that you have in a given data will be negatively correlated with each other, or they will be positively correlated with each other. Now, either it will be negative closer to -1, or it will be positive closer to +1. Both are not good for our data. Why I am saying so? Please try to understand. For example, let's say I am saying that we will be having two features. Let's say feature F1 is there. Maybe they are responsible for predicting the house itself, right? So let me try to plot it once. Let's say I will be having a feature F1, and here I will be having a feature F2. If I am saying that at any point of time, when the value of F1 is increasing, the value of F2 is also increasing. Means something like this. They're directly proportional to each other. At any point of time, what you are observing a trend is that at any point of time, when your value of F1 is increasing, for example, let me give you some real-time example. Maybe let's try to understand the relationship between the weight and the height of a person. So what we can observe, as the, let's say, height of a person will increase, it's a very simple example which I'm trying to convey here. You will observe the common form is that in the maximum scenarios, the weight of a person will also increase. So in this way, you can say that, okay, these two variables, these two features are highly correlated with each other, and that is in a positive direction because they're directly proportional, right? This is the meaning of highly correlation in a positive direction, means the value is approximately very close to +1. Now, what is the meaning of negative correlation? The simple meaning is that at any point of time, if let's say you will be having feature F1 and then you will be having feature F2, what you are observing is that as the value of F1 is increasing, your value of F2 starts decreasing. It's kind of an inverse proportion which you are observing here. That as the value of F2 is increasing, what you are observing, the value of F1 is decreasing and vice versa. Means value of F1 is increasing, value of F2 is decreasing. So this kind of format you're observing between these two features. Again, if you will be able to observe, in a way they are correlated, but now they are negatively correlated. Means in this case, in this scenario, their value is approximately equals to -1. Now, what in layman terms these things indicates? Let's try to understand this fact. It simply indicates that these two features are trying to give the similar kind of information. Please try to understand my statement. These two features are trying to give a similar kind of information which is responsible to give the predictions. So what usually happens is that, let's say we will be having features of F1, F2, F3, let's say F10. And let's say we will be having a target value which is available. Doesn't matter whether we are trying to solve a regression based problem or a classification based problem. But yeah, this is what we have. So we will be having a features and then we will be having a target values available. Now, when I'm saying that the feature F2 and let's say feature F9, they are highly correlated. They are highly correlated. Doesn't matter whether it's positively correlation or it will be a negative correlation. I am saying that these two features are highly correlated. Means they are trying to convey a similar kind of a pattern, similar kind of information, which is responsible to give this target value, which is responsible to give this target predictions. So that's why what we usually try to take only single feature at that point of time rather than taking all the features. So it's kind of a feature selection technique, you can say. This is a kind of a feature selection technique, right? Because too many features are not helpful if they are conveying the same kind of information. So rather than taking all the features, which will increase the complexity only, what we will do is we will try to select only those features which are giving me a very important information which not other feature is giving to us. Okay? So let's try to now focus and jump towards looking towards this correlation coefficient value. I hope that you will be able to understand my point. What is the inference behind, doing the calculation of a correlation coefficient? I hope that now it is pretty much clear to each and every one. So without wasting any time, let's try to, do the calculation and the, function calling for that. So what we can do is we will be having a data set dot. Now this is the function which is core. This function will basically helps me to give a chart, or you can say to give a proper feature names with respect to every feature. It will give in a tabular structure what is the correlation coefficient value. So this is the simple way to do the calculation. No hustle here. So here, if you will be able to observe, once I will run this code, you will be able to see that all those features, same features, if you will be able to see, they are obviously highly correlated because med inc and med inc, they are both the same, and obviously their values will remain the same. It's kind of a +1. That's why if you will be able to observe diagonally, all the elements values are +1 only, because obviously they are highly correlated because they are having the same features only. But on the other hand, if you will be able to observe house age, mad inc, average rooms, house age, for every particular two features, now you will be having the values which ranges between the -1 to +1. In this complete table that we have, you just have to understand that is there any two variables, two features which are having a highly correlation coefficient. That is what we have to understand. Here, if you will be able to observe, apart from this diagonal one, which doesn't make sense for our code, when I'm talking about the independent features that we have, as of now, I can't see any feature, any value which is having a very high positive or negative correlation coefficient. I think I am correct. But still, if you will be able to get that at your end, you can let me know. But yeah, here, as far as I can see, that there is no as such a feature which is having a very, very high, like whose value is more than 0.80 or 0.85 correlation coefficient value. Maybe average bedrooms, you can say, and average rooms, they're having a highly correlation coefficient. It's 0.84. Usually 0.85 plus is considered, but it depends again on dataset to dataset, that you can try to see that if you will try to remove one variable, maybe average bedrooms, does that performance is impacted or not. But yeah, this number I can see here. Apart from this, any big number I can see? I don't think so. Okay, longitude and latitude. Again, they are having a very high correlation coefficient. right? Negatively correlated. Now here you will observe one thing, right? When we are talking about average bedrooms and average rooms, again, obviously they are conveying a similar kind of information only. In a given house, average number of bedrooms, average number of rooms are trying to convey the similar kind of information. That's why you will be able to observe they are having a very high correlation coefficient. Similarly, the same thing will go for longitude and latitude kind of a correlation coefficient, right? Apart from this, we can also create a pair plot which will be able to give us for all the features that we have, what is the correlation again they are trying to convey. So what you can do is you can take the help of this SNS library which we already have imported. You can say pair plot, and here you can pass data set. Now what will happen after some point of time, you will be able to see that there will be a complete end-to-end chart where for every two features you will be having a plotting that will also represent that what kind of distribution every particular variable or the feature that we have indicates. But until so far, what inference we will be able to get in the above cases, the first important thing is what we will be able to observe, that we have observed average bedrooms and average rooms have high correlation coefficient, and the value is 0.847621. I'm just writing it down. Also, we have observed that this longitude and latitude are negatively correlated with this number. So let me write it down this as well. Longitude and latitude, they are also negatively correlated. It's minus of this thing. Let's try to write it like this so that we will not get confused later, right? So it means that between these two features, average bedrooms and average rooms, and longitude and latitude, we can take a single feature also that will also work and will give a sound performance. Okay, we'll take care in this in future. Apart from this, I don't think that there is any other feature which is having a higher correlation coefficient. But still, I'm looking into it. Maybe we will be able to get any other feature. Meanwhile, I think the below code is running up. But I don't think we do have. Perfect. So here, if you will be able to observe, finally, now we will be able to get a pair plot. Here, if you will be able to see, if I'll just zoom my screen, for every feature, for example, Madden is in the y-axis, house age is there, right? Average rooms are there, average bedrooms are there, population is there, average occupation is there, latitude is there, longitude is there, price is there. And then on the x-axis again, there are feature names which are available. So what we will be able to get here is the graph for every particular two features that we have, kind of a pair plot. That's why it is called as. And you can see that whether the values are directly proportional or they are inversely proportional or they are scattered somewhere, outliers are there or not, all these things you will be able to see. For example, let me give you one simple example. What is the meaning of an outlier? Some exceptional points are something which we can say is an outlier. For example, here if you will be able to see, corresponding to average bedrooms and you can say population. Can you see the topmost two dots? I can apply the cursor here. Topmost two dots. So these two dots, right? So here if you will be able to observe, this is something which we called as the outliers, which you can see somewhere dots are there. Many points are surrounded by one region, and then there are 1-2 dots which you will see outside another region. That is something which we call as an outlier in every graph. Okay, when we're talking about these outliers, there is another way to detect that, and this is something that we called as a box plot. Again, it's a concept in statistics which is basically used to detect the outliers in a given data set. So how basically we will be able to do that? You will be able to say figure and the axis AX, you will try to call this PLT dot subplots, and here you can define the figure size, like how much size of that subplot of box plot that you want. Maybe I want 15 comma 15, so you can refer that pretty well. Now what you can do, you can call this sns.boxplot. Inside this, you can refer what kind of data you want as a box plot. I want data set here, and the axis is AX, which I have already defined in the above part. If you want, you can also save your figures on the go. For example, if you will say plt.savefig is the command to save the figure values, and here you can say it is a boxplot.jpg. You can also save in the form of a PNG. Anything will work here. Just run this, and once you will be able to run this, you will be able to see that a complete graph is also available here. If you want, you can download this as well. Okay. And once this is downloaded, you can grab this in the downloads, and you will be able to see this is the box plot which we will be able to get, right? Now here again, you will be able to observe that we will be having medinc, we will be having house age, we will be having average rooms. In the x-axis, try to observe whatever be the values are there, right? Population is there, average occupation is there, latitude is there, longitude is there, price is there. One thing which you will be able to observe very clearly here is that, all the values apart from population is lying under the range from 0 to maybe 500 maximum, I'm not sure, but the range is very, very small. Every other feature apart from population, and that creates again a bias, right? So what usually happens when we will be having something like this kind of architecture, please try to understand this from this box plot, what I'm trying to convey here. So usually what happened is that you will be able to observe apart from population. So population is having a very bigger range. Just now we have observed. And that makes sense also, because we are talking about that in a particular block, what is the amount of people living there, right? So population is having a very huge range of numbers. That is what we have seen in the box plot as well. And even this population contains outliers also, which you have observed. They contains more outliers. So here, if you will be able to see how you can detect those outliers, if you will be able to see all the points above this line, dash line. So this above dash and below dash is a range. Outside this range, if there is any dot, any data point which is available, all those data points will be considered as an outlier. Okay? So now the important point here is that we have to somehow manage these outliers. Either one way is you can remove these outliers in a simple go, but obviously that includes a loss of data points. Other way is you should know the concept of quantiles. Within 95% quantile, you can take the data points, and remaining you can get rid of. That will try to remove the major outliers present in your data set. Few outliers, if they are there, that is completely fine, because they can act as a noisy points, and it will make your model more better in a way that it will be able to detect that, okay, these are the noisy points, and I don't take those points in a prediction part. But more of them is not something which is recommendable. Now, here, if you will be able to observe this data point, when we are talking about this population, they have a very huge range of numbers. Whereas the other values like average number of bedrooms that we have, or average number of rooms that we have, although they are representing the similar information that we have seen from the correlation coefficient, or we have something called as mad inc as the feature name, or we have something called as a house age as the feature name. All these are somewhere surrounding within some specific range, but this range is very, very high. Now, what usually happens when you directly impose this kind of a data set directly to the model, maybe what we will do is in the future, we will apply a linear regression model here, right? Or maybe any machine learning model. Today, we are discussing the machine learning model as a linear regression, but in future, we will discuss more models also, right? So what I'm saying is, you will apply any machine learning model here. Maybe today we are applying a linear regression. So what happens is that our model will get biased towards treating population feature as on priority. As on priority. It will give more priority towards population values because the numbers are very big, right? So it will automatically, inferent that, okay, population is having a very big range of numbers. Might be this feature is having a utmost priority as comparable to other features. But that is not true. All these features, apart from the features that is having a very high correlation coefficient, apart from that, all those features are having a equal relevance in order to give the predictions. So what we have to do is, in that scenario, we need to avoid this bias. We need to avoid this bias problem. And to avoid that bias problem, we need to do a standardization. Or you can say, you need to do a normalization of all the values that we have. We need to do a normalization of all the feature values that we have. All the feature values that we have. So what usually happens is that we will try to scale our values in between some specific range, all the values. And that is where we have two methods. One way to scale the values is via using a standard scalar. Standard scalar. Another way is you can use a min-max scalar. Min-max scalar. Now, what I will do is, I will try to do with the standard scalar as of now. What it will do is, it will try to convert all the values in a standard normal form. In a standard normal form. Now, I hope that everyone knows what is the meaning of a standard normal form, where the mean value is 0 and the standard deviation value is 1. So this is what we will try to do. We will try to convert and scale our values in the form of a standard normal form by using the standard scalar. So this will help my complete data points within a scale, within some specific scale. So that is where what we will try to do is, we will try to scale our data points. Now, to do that, what we will do, we will try to first of all split our data points into two important components. One is the independent features, another one is the dependent features. So what we will do is, we will try to do one thing. We will try to split the data into independent and dependent features. So what we will do, I'll take the variable x. There I'll take the data set completely, apart from the last column that we have, which is price, right? So what I will do is, I will try to take all the rows and I'll try to take all the columns except the last one. This is x. What is y, which is the target one? Here I'll try to take dataset.ilog, right? We are taking with the help of the index numbers that we have. And here I'll try to take all the rows and only the last column. Okay? So let's try to see what we will be able to get from this part. If you will be able to observe the value of x, you will be having all the rows, all the columns except the last column, as you can see, because we have taken all the rows except the last column. Let's try to show you the value of y as well, which is a dependent feature that we have, which is the price. And here you can see we will be having the price values available from 0 index to the 20,639 index. Now what we can do here is, we can try to split our data into training and testing, and then maybe we can do the scaling process. So what we can do is, we can split the data into train and test set. So what we can do is, we can try to say from sklearn underscore model, sklearn dot model underscore selection. What we can do is, we can import here train test split, because we want to do a split here in the form of a training and testing set. So what we can do, we can say x train, we can say x test, Then we can say y train and the y test. Now what I will do here is, I'll try to say train test split, and inside this what I'll take is, I'll take the value of x completely, the value of y completely. What is the test size you want to take? Maybe I want 30% of my split is in the test set, and remaining 70% will be available in the train set. After that, if you want, you can also define the random state, so that we all will get similar kind of a output. Let's say ki I will take a random state as maybe 42, so that we will be able to get the similar answer. The importance of this random state variable is, for example, if you will not apply this random state at each and every point of time when you will run this code, you will be able to get a different set of a training data, different set of a testing data. If you want to fix that number, that you will get at every time when you run the code, similar set of a training and similar set of a testing set, so that's where a random state will come into picture. You can apply this with any number, 42, 144, 146, any number, and you will be able to get that set value. Okay. Once you run this, let's see what our training data will look like. Perfect. Now you can see how our testing set will look like. Shift plus enter will be required to run the code. Similarly, you can see how basically your Y train will look like. Corresponding to those training sets, you will be having the price value. Similarly, you can test how this test set will look like. Corresponding to every test value, you will be having the value of a test set. Now, what you can do is, now here comes the step of doing normalization of the given data points. Normalization of a given data point. So what I will do is again, this is a part of a pre-processing. So you will say from sklearn dot pre-processing. What you will do is, you will import standard scalar, because that is what you want to do. You want to scale your values in the form of a standard scalar form, right? So you will call this function and store this inside the variable standard scalar. Okay. And then finally, what you will do is, you will say x train. You can say norm, because you will be able to get the normalized values. What you will do is, you will try to take your scalar dot, you will use this function fit underscore transform, and inside this you will call your values x train, which you want to transform. This will help your values to fit or to scale within a specific range. I'll show you the same thing as well. Now, if you will be able to observe this x train underscore norm value, you will see the difference. Can you see a specific range is there? In more clear sense, let me try to again do this box plot, and we'll try to show you the range now. Because you will now, when we visually see the things now, then we will be clearly able to understand what things are happening. So I'll try to show you. X train norm. Box plot of a train data. Let's see. Can you see? A big difference is there, right? Now can you see all the boxes in the box plot lie in one range? Can you see that? There is a gap between this chart which we get now and the previous chart that we got, right? There only the population is having some another level, remaining are of similar level. But now if you will be able to observe it visually, you will be able to see a huge difference. A huge difference is there, right? Although outliers are there, we will discuss in the upcoming sessions that how we can deal with the outliers. There is a complete concept of quantiles which I will taught, and then we will see that how we can get rid of these outliers. But as of now, I'm not focusing on that aspect. I'm focusing on that how basically we will be able to scale the values so that our model will not be biased towards any single feature. That is the ultimate thing which you have to understand it here until so far, right? Now here, if you will be able to see, I have used one function called as fit underscore transform. In the test set, what usually happens is you have to use a function called as a only transform, scalar dot transform. And here, what you will do is you will use this on the x test. You can say x test underscore norm. So this is the normalized values of a test set, similar to the one which we got as a train set, right? If you will be able to see, the similar plot you will be able to get for the test set also, the box plot. X underscore test underscore norm. And here you can say box plot of a test data. If you will run this, now again you will see a similar kind of a distribution will be there, where the range of every particular feature that we have is quite same, right? So we will be able to normalize our data values, our feature points within some specific range. That is what we have understood here. Perfectly fine, perfectly fine. One thing now if you will be able to observe is that in the train set, when we are doing the normalization, I was using a function of fit underscore transform, right? On the training set that we have. Whereas in the test set, when I was doing the normalization, I have only used the transform function on the test data. Now, in an interview, interviewer can ask you why usually this happens. That in the training set, it's always recommended to go and use fit underscore transform function when we are doing a normalization. And on the test set, it's recommended to go for a transform function. What is the significance for that and why we are using this kind of a thing? So I'll talk about this particular thing in the next upcoming session. I think this session is already quite long, but this is your assignment task. Please try to explore that why I am doing so. On the training set, I am using a fit underscore transform function. On the testing set, I am using a transform function. And we will continue from here itself in the next upcoming session, where I'll discuss about the reason behind the same, and then we will further move towards the model training part, where we will see that now once we will do the EDA part, how we will be able to apply the model training, the linear regression algorithm on the top of this kind of data set. I hope that you are enjoying this complete session because it's complete practical session, and I am doing all the code demonstration also in the live part itself, so that no one feel bored here. If you still have any sort of doubt, do let me know. I will for sure try to resolve it as soon as possible. Hello everyone, welcome to the session. So now in this video, we'll continue our previous discussion, where if you remember, we have normalized our data of training and the testing set into some range. And the reason behind that is because we have seen that population is one feature that we have in this house price prediction data set, which can create a bias when we are doing a model prediction or when we are training our model, right? In order to avoid that, what we have done is, with the help of a standard scalar, we have tried to normalize our data points in the training set as well as in the test set. And if you remember, I have given you one assignment, or you can say homework, to explore on your own that when we are doing the normalization part in the training set, I have used a function named fit underscore transform, whereas in the test set, when I was doing normalization of the values of a given feature names that we have, I have used the function named transform. And I told you that in an interview, interviewer can ask from you that why usually this will happen. Why in the training set we are using fit underscore transform function, whereas in the test set we're using a transform function. What could be the possible reason behind the same? So now I hope that you already have explored and you already have something in your head before I will give you the explanation. Let's try to understand this point very clearly, and then we will move ahead in the next upcoming part of a model training phase. So what usually happens? I talked about a standard scalar, right? So we have applied here standard scalar in order to scale our values. Standard scalar. And in the last session, I have done the implementation. I hope you have clearly seen that and you know that how we can do so. Now, what usually happens, I told you in the last video itself that, basically it tries to give us a data in the normalized manner, or you can say in the standard normal form. Instead of writing normalized manner, I should write standard normal form. Now, if you have a clear-cut idea about the concepts of statistics, you will be clearly aware about the idea of a standard normal form. Standard normal form meaning that we will be having a mean value as 0 and standard deviation value as 1, right? This is the meaning of a standard normal form. The question is how we can convert given data points. If I'll provide you a set of feature values, numeric data points, if I'll say how will you able to convert that into a standard normal form, what will be the formula to do that? So the answer would be, it will be done by the z-score. So it will be nothing but what is the value of xi minus mu by sigma. Means anyhow what you're supposed to do is, you need to compute, this is something which is nothing but mean, and this is something which you can say is the standard deviation, right? Standard deviation. So what does that mean? For a given set of feature values, first of all, you need to compute the value of a mean as well as the value of a standard deviation. Now, for every feature value that you have, maybe you have number of bedrooms, you have average number of bedrooms, you have so many features, right? So basically what you usually do is you will try to get that value of a mean and the standard deviation for every particular feature which we are considering to go into the training phase. Now what we will do is, this is something which we call it as a fit. So what is the meaning of a fit? When you are saying that in the training set, you are applying a function named fit underscore transform. That is the question, right? In the training set, when we are doing a standardization, we are applying a function named fit underscore transform. The question is what this function is doing. This function is composed of two tasks, fitting and then transforming. So when we are saying we are fitting our model, means you are trying to compute the value of, for every feature that you have, what you are doing is you are trying to compute the value of mu and sigma. You are trying to compute the value of mu and sigma. And then when you are saying transform, what does that mean? The simple meaning is you are trying to transform all the given values by applying that formula, z formula, right? So here you will try to get the normalized values by applying that z value formula, right? Which needs the value of mu and sigma. I hope you will be able to understand. So now that's why in the training set we are doing fit and transform. Whereas when we are talking about a test set, what we are doing, because now in the training set we have already the values of mu and sigma for every feature value that we have, that same value we will try to apply and we will just do the transformation. Means we will just do the finding of that z value with that mu and sigma, because we don't want to change the properties of a test set, and that is very important to understand. So that is the only reason that why in the training set you will always observe in machine learning we are applying fit underscore transform while doing the standardization, and in the test set we are only using a transform function. That is the only reason. I hope now you will be able to understand that part pretty well, and you will be able to explain the same thing to the interviewer as well, right? Now let's move ahead to the next important part, where the next important phase which we are starting is the model training, right? Now what model we want to apply is a linear regression. So let's start with the next phase, which is a model training, which we want to do. Here what we will do is, first of all, obviously we need to import that model. So what we can do is we will try to import our model, which is available in linear underscore model. So what we can do, we can say from sklearn dot linear underscore model, we can import model name linear regression. After that, what you will do, you will apply this linear regression method, right? And then what you can do is you can fit your training set, that normalized values, into this. Now what you can do is you can say regression dot fit, and here you can pass your x-train norm values that you have and the y-train data, which is corresponding to every data point that you have the final actual predicted value. One important thing is, as of now, if you will be able to observe, we have not removed any of the feature value, right? But when you will be doing this task, please make sure that it would be great if you can remove any one feature out of this F room and F bedrooms, because they will be having a higher correlation coefficient. Try to see the performance. I am doing this by considering all the metrics, so you will be able to see the performance of the model here only in the sessions itself. Then what you can do when you are doing this task, try to remove, drop any one of the feature, maybe F room and average number of bedrooms. Similarly, out of this latitude and longitude, any one of them you can try to remove. As of now, we are considering every feature, but it would be great, I believe, that if at your side, what you can do is you can try to remove the features which are having a high correlation coefficient that we have seen. Average bedrooms, maybe you can remove, and longitude part that you can remove. Okay? So let's try to fit our model now. Let's do this. So this is done. Now what we can do is we can see the coefficients that we have in the regression model that we have. So what you can do is you can say print regression dot coefficient, and here if you will be able to see, you will be able to get the values of the coefficient of the regression. So what is this all about? If you will be able to see how many values you will be able to get, it will be 1, 2, 3, 4, 5, 6, 7, 8. Why is that so? I hope you will be able to understand this point very clearly, because here if you will be able to observe, we will be having 8 features, right? So how the equation of that straight line will look like in a linear regression? Obviously, when I was doing the explanation, I have talked about y is equals to mx plus c, right? Considering that we have only single feature, but in practical real-time scenarios, obviously we will be having multiple features, right? So the equation will look like, because we will be having 8 features, it will look like m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 plus m5 x5 plus m6 x6 plus m7 x7 plus m8 x8 plus c. So here if you will be able to observe how many independent features we have, 1, 2, 3, 4, 5, 6, 7 and 8. So in a way we will be having 8 independent features, right? So corresponding to every feature, I have taken obviously the values. So this is a coefficient. So when we are saying we are trying to evaluate the coefficient values, it means what we are getting in that list. So what we are getting in that list is something which is the value of m1, m2, m3, m4, m5, m6, m7 and m8. This is what you are calling it as a coefficients of the regression model that you have. That is what you will be able to get in that code part, right? Okay, this is something that we call as a intercept. I hope again everyone knows this part as well. This is what we call as an intercept, and all these things are the coefficients, right? So what I can do is I will try to show you the intercept as well. It means intercept will always remain the one, but the number of coefficients will depend on the number of features that we are looking into, or the features that we have in a given data set, right? So let's say if you will remove the features which are having a higher correlation coefficient, and by removing that, let's say you are having only 6 features currently when you are training your model, then obviously when you are trying to get that coefficient value, you will be able to get 6 different values of m1, m2, m3, m4, m5 and m6. I hope my point is clearly understandable to each and every one here. So what we can do here is we can try to print the values of now, what we can say intercept. So what we can say regression dot intercept, underscore. So once I will do this, you will be able to see, we will be able to get the values of the intercept now, right? I hope it is clearly visible to each and every one. So this is all about the model training, which is done. Now in the next upcoming session, we will try to see how we can do the model prediction. Okay? We will try to see how we will be able to predict our data, means the price of the house, given the testing set that we have, right? We have split our data into training and testing. So on the training set, we already have created our model by the name of a regression, which you can see here. We have trained it pretty well. We got the coefficients values, we got the intercept values. Then now the next important phase is to check the model predictions, that whatever model we will be able to get, whether this model will be able to give us the predicted price value or not. That is what we need to see. So stay tuned. Hello everyone, welcome to the session. So now in this video, we'll do the model prediction. So I hope that you remember that in the last video, we are done with the model training part. We have trained our model with the linear regression algorithm, and the model name is regression, right? So let's try to do the prediction on the test data now. So what I will do is I'll try to take the model name regression dot predict, and what I want to do the prediction is on the test data, right? So what I will do is I'll try to take the test data, and maybe I'll store my predictions in the variable name rig underscore pred. So this will give me the predictions of the test data. So what I can do, I can just try to see what is the outcome we will be able to achieve. So here, if you will be able to observe, okay, one thing which I have done wrong is my prediction, my test set is x underscore test underscore norm, if you remember, right? We have taken the normalized data. So let me update this. I think now it is fine, right? So we will be able to get the predictions, which is a price house, right? House of a price, which we will be able to get there. Now what I can do here is, if you remember, when I was explaining you the concept of linear regression, I have explained you what is the meaning of residual, or what is the meaning of an error. Do you remember that? What I have explained you in the explanation part? The difference between the actual value and the predicted value. As it's a supervised machine learning algorithm, we do have the actual y-test data, and now we do have the predicted data. So what we will do is, we will try to calculate the residual. Let's try to calculate the error, or you can say the residual. Okay, let's try to see how will it look like. So I will take a variable name as residuals, and what I can do here is I will try to get the difference between the value of a y-test and the value of the reg underscore pred, where I have stored my predictions. So what I can do is I'll try to run this particular part, and we'll try to see how my residuals will look like. So you will be able to observe that for every index number, we will be having some residual value, which is in a negative form, which can be in a positive form, right? To see how will it look like, what we can do is we can try to create a distribution plot of these residuals. So let's try to create a distribution plot of the residuals. Now, usually as per the conditions and as per the assumptions of linear regression, do you remember how the residual will look like? It should be in the form of a normal distribution. The more it will be inclined towards normal distribution, better it means that our model will be trained, right? So let's try to see how this plot will look like. So our way to implement is sns.dist plot. Dist plot will help us to give the distribution plot of whatever data we want to see. For example, I want to see the residuals. And what is the kind of plot I'm looking for? I am looking for KDE, kernel density estimation. So this will give me a plot. And here, if you will be, let me just figure it out. Kind is equal to KDE, if I'm not wrong. And the variable name is residuals, right? Let's see again. This plot, the spelling is wrong. Now I think it should be fine. Can you see that we will be able to get a normal kind of a distribution, but there is more inclination in the chart towards the left side. It means that we do have, I can say a lot of, you can say outliers are there, where we will be having a value from -10 to -2 as an error. But the maximum part of our data points belongs to a residual, which is from -2 to +4, if you will be able to observe here, right? It belongs to -2 to +4. So that is the real idea, and it clearly indicates that yes, somehow our model is going in a correct direction. But yes, there is a need to improvise on top of the outliers that we have seen in the population data. If you remember, as of now, I have just shown you how we can detect that. We didn't work upon on improving those outliers or handling those outliers, which I will demonstrate in the upcoming sessions. But yes, there is a lot of scope in EDA. That's why this kind of graph is there. Otherwise, it would be in a proper sense in between the normal distribution, just proper Gaussian based distribution that we will be able to get if you have done the EDA in a proper way. Okay. Now, this is done. We will be able to get the predictions pretty well. The next important part which we have to see is the, model evaluation, or you can say the performance of the model that we're supposed to see. Now, in order to see the performance, we have lot many metrics. For example, in the explanation part also, I have talked about what is MAE, what is MSE, what is RMSE, right? Mean absolute error, mean squared error, root mean squared error. Then what is R square, what is adjusted R square? All these things we have to evaluate. We have to see what are the numbers we will be able to get. So what I will do is I'll try to create a separate video for that, where I will try to check upon all the performance metrics that we have. We'll try to see what is the number we will be able to get from there. And finally, in the very last video, I will show you that how we will be able to save this model, so that at each and every time we don't need to, do the reiteration, retraining again and again. Okay? So with this, let's end today's video. I'll see you all in the upcoming video, where we will talk about the different model performance metrics in a regression algorithm. Hello everyone, welcome to the session. So now we have reached to the stage where I think it's a good time to discuss about the performance of the model. Until so far, we have already trained our model. We have seen the predictions of the model as well. And we have created a distribution plot for the same, where, the residuals that we have find it out with respect to the difference between the actual value and the predicted value. We have seen that it's a normal kind of a distribution, but yes, on the left side, there is a kind of outliers which are very clearly visible, right? Now, let's try to see the performance of this model via the different metrics. So if you are following from the very start of the session in this course, I have already talked about the two interesting metrics that we have in a regression algorithms, which is MSE and MAE, mean squared error and mean absolute error. And I have already talked about what is the difference between these two. So obviously, I'll not go into the technical details for the same. I'll just try to show you how, in terms of implementation, we can, directly fetch from sklearn this metrics, and we will try to see what numbers we will be able to get in this. Okay? So let's try to see from sklearn dot metrics. What we can do is we can simply import what we want to find out. Firstly, let's say I want to find out the mean squared error. So I can just fetch that mean squared error. Similarly, if I want to find out mean absolute error, I can directly fetch that as well, right? Let's say I want to calculate what is R square. So again, this R square, I already have conveyed in the previous video. So if there is someone who is not having the technical understanding of these keywords which I am mentioning here, please go and refer that videos which I already have discussed, and then come to this implementation part, okay? Because I'll not discuss these things again and again in terms of technical part, okay? Now, what we're supposed to do is, let's say I want to print what is the mean squared error I am getting here. So what I will do, I'll say mean squared error. And obviously, in order to calculate the mean squared error, we need the actual data and we need the predicted data. So you know that the actual values are available in the y-test, and the predicted values that we have stored is in the variable name, I think, reg underscore pred, right? Regression predictions are there. That's why I have named it as reg underscore pred. Similarly, if you want, you can print what is the value of a mean absolute error, right? Similar to that, you can just write it down. What is y underscore test and what is reg underscore pred again. Similarly, let's say we want to print what is the R square score that we will be able to get. So you can print that as well. You can say print R2 square score, right? And here again, you can mention these two values, which is what is the Y test and what is the regression predictions that we will be able to get. Now, once you will run this particular code, there is some issue that we are getting here. Mean squared error. Is there any spelling wrong? Yes. Mean squared error. I think now it should be fine. Yeah. So here if you will be able to observe, we are getting the mean squared error as 53%, mean absolute error as 52%, and the value of R square score is 59%, right? So what we want in our actual terms, obviously what we are looking for is a lower error value, whether it be a MSE or MAE, right? MSE and MAE both are indication of the error values, which should be very, very less. And we are looking for a higher range of values, maybe bigger than 0.7 or 0.8, approximately maximum it can be 1, right? Higher value of, you can say, R square score and adjusted R square score, right? Both we are looking for a bigger value. So obviously here if you will be able to observe, the values are not that much closer to 1. The only reason is that in EDA part, there is a lot more stuff which we can do, which we can add on, as I already stated you while showing you the EDA part implementation, which I hope that you will do at your home. And maybe that can improvise these numbers, right? Similarly, if we will be able to see in the upcoming sessions how we will be able to remove the outliers, then again, that will help this performance metric to improve. So there is a lot more things to do. That's why this number is there. As of now, because it's the very first session, I don't want it to be implementation heavy. That's why I have taken it very smoothly, very easily. But in the upcoming sessions, you will see that at each and every time, we will keep on adding few more stuffs in EDA, so that you will be able to understand that how we will be able to get a better results, right? Better predictions that we will be able to form. Now, let's say you want to form the value of adjusted R square. So I hope you already aware about the formula of doing the calculation for adjusted R square, which is 1 minus what is the value of a R square score. So what you can do is, you can do one thing here. Maybe you can store this number inside this score value, right? And that score value, you can use it here. If we will be able to see now, x underscore test underscore norm. So please refer the formula of adjusted R square. So this is the formula to calculate the adjusted R square, which I already have referred again in my previous video. If there is anyone who is not aware about how we usually evaluate the adjusted R square, what is the difference between R square and adjusted R square, please do refer the previous videos where I have conceptually illustrated all these things. It's just the implementation I am showing to you. So what is the issue here? Let me just check it out. What is this x test norm dot shape looks like to me? Let's see. So it is fine. It is 6192. I'm taking the number of predictors, which is, that's why I have taken the number as 1. Perfect. Minus 1 n minus k minus 1. So what mistake I am doing here is, if you will be able to observe, the score variable value we are not inserting actually. So if we will print this score, we will not able to have anything here, right? That is the issue we are facing here. The mistake is I just copied it out, and that's the bad idea, to copy the things. That's why I usually prefer to write also. So here now I think score variable will have some value, and now it should, you know, do the job properly. Now here if you will be able to see, we will be able to get the value of a adjusted R square as well, which is almost approximately, if you will be able to observe, equivalent to the R square score which we are getting, right? So in this way, we will be able to get the numbers for MSE, MAE. If you want, you can also work upon calculating the RMSE. You, I hope, are already aware about the fact that the only difference between R square and MSE, RMSE and MSE is that we are doing a square root of that. So if you want, you can just print that RMSE value also. What you need to do is, the only thing that we're supposed to do on top of this is np dot square root, which we will take, and then I think the things will be fine. This will be able to give me the score for a root mean square as well, root mean squared error as well. So in this way, we will be able to evaluate all the performance metrics that we have in a regression part. Now, the only thing which is pending here is that, okay, how we will be able to save the model. For that, we should understand there is something called as a pickle file. I'll talk about this in the upcoming session, that how we can save the file, and then in future, if let's say I want to open that file and want to gain the, predictions with respect to that file without doing the training from scratch, how we can do so. See, in real-time scenarios, always remember that you will deal with a huge amount of data. And training requires a lot of resources, right? As of now, we are dealing with a very small amount of data. And that's why training happened very instantly in the recording itself. And intentionally, I can't pick up a huge data as well in the recording part because it will take time, right? But in future, obviously, we will take a bit of huge data where I'll show you that, how you can use your runtime type from CPU to GPUs. And if you will take a Collab Pro, it will provide you higher configured GPUs as well. But as of now, what I'm trying to convey here is that if the file size is bigger, training takes a lot of resources. And what I want is, I don't want to use these resources again and again. Let's say in future, for more test data, I want to do the prediction. The bad idea is that you will start training again. Sometimes what happens is, if your data set is of image data, it can take 2 days, 3 days, 1 week, 2 weeks. So will you do the training again? No, not at all. So in practical real-time industry per se, we usually try to save that model in the form of a pickle file, and then we will use this pickle file in future in order to grab the results on the test data. So how we can do that? It's a very, very important step, which I will share in the upcoming video. So stay tuned. I hope that you will be able to get the understanding until so far. Hello everyone, welcome to the session. So now in this video, we will try to see the final step where now we have the model. We have already seen how the predictions are going on, how the results are coming up, right? Now let's try to see how we will be able to save the model. It's not only for the linear regression per se, be it any model in future. Obviously, after training our model, as I told you, we need to save that model, right? So that in future, if let's say I want to do the prediction, I can directly use that model file, pickle file, and directly I can get the predictions done. Okay? So what we will do is, we will try to first of all import the pickle. Okay? What we will do is, we want to dump this file. So what we will do, we will try to use this function as dump. So usually what happens is, this pickle file will also be used for the model deployment per se. So whatever be the, cloud-based platforms we will use for the deployment part, right? Or we do it locally as well. At that point of time, obviously we need this pickle file only, so that whenever the actual test data will come, that will hit the pickle file, and with the help of that, we will be able to get the predictions, or our model will get the predictions. How will it happen? Let me show you. So what I am doing is, my file name, my model name is, I think, regression. If I'm not wrong, let me just verify. The model name is regression. Yes. Now what I want is, I want to save it. So what I will do, I'll say open. You can give any name. Maybe I will give model.pkl is the extension for the pickle file. And in which mode you want to save it? Obviously, because we need to dump it, there will be a write mode. So WB. Okay. Now this will be done. Once it will be done, you will be able to see that on the left side of my screen, there is a model.pkl file. You can download this file and you can store it. Whenever we will talk about the deployment part, at that point of time, we need this pickle file to deploy and get the results done. Okay? But to show it here itself on the Collab, what usually happens? Let's say in future, I want to do the predictions of this regression algorithm. So what I will do, I will take this file itself. So what I will say, the function will be pickle.load. So always remember, when you want to save this file, dump is the function. When you want to load this file, use this file, load is the function. Now you will open this file again by giving the name as model.pkl. Just now we have seen it is available in our collab. After that, the mode will be write mode, because here I don't want to write something. I want to read that file. That file will contain the coefficients. That file will contain the intercepts actually. And with the help of those values only, my model will be able to give me the predictions. So if someone can ask you in the interview also that, okay, you are storing this pickle files, but that actually what things are there in the pickle file, you can say these are nothing but the coefficients that we have for this model with respect to linear regression algorithm, the intercepts that we have, with the help of which, if let's say in future you will provide me the feature values x1, x2, x3, x4, x5, xx, I have the value of m1, m2, m3, m4, m5, m6 and the c. So I will be able to get the test data, which is test output, test prediction, which is the house price value, right? So now what I will do, I will be able to load this first. Once you will be able to load this, it is taking some error. Let me just check it out. Open. I think there is some bracket issue. Just wait for a moment. Open model.pkl. Okay. It should be 2 brackets here because it is taking 2 arguments, right? So now it should be fine. Once we will be able to load this file, what we have to do, let's say we will be having the dataset as original dataset is dataset, right? What I will do is I'll take the 0th data, what that contains. What is our dataset name? Just give me a second. Let me just verify from where we started. Okay, housing is the name. Okay. So what we will do is we will try to take a housing that bunch dataset. This is an array, right? It means it contains few numbers, which is 8.3252. Every feature name is containing some value. Let's say I want to do the prediction of this particular house price. How can I do? So obviously, first of all, we need to do the scalar dot transform to transform these values and scale it in one go, right? So what will happen? Let's do this thing. You will be, okay, we need to reshape it so that we will be able to form it in the way we have done it now. So it will be 1 comma minus 1. Once you will be able to transform, let me just check it out, how the data will look like. Can you see? Now it is in the form of, the format is like what we want. Here, if you will be able to observe whatever values we want in the specific range, we will be able to see that. It's not that population is having a very higher range. And let's say I want to do the prediction of this data, model.predict. So what will happen? Let's see. You will be able to get the value, which is a reasonable value, right? You will be able to get the data, which is giving me the house price prediction. So this is how basically, if you will be able to observe, now I have not trained any model, by the way. I have just loaded my model. I have just loaded my pickle file, and I have just used that pickle file, that is the model, to get the prediction done. Similarly, you can use your data frame data also. So it contains the data points directly, which is in the form of, I would say, X test norm, if I'm not wrong, right? X test norm. So let's try to do one thing. Maybe what I will do, I'll say model dot predict. This is the normalized values. Let's see what we will be able to get here. So can you see, we will be able to get the, again, predicted values of all the house prices, 0.7260 something something. If we'll go back, the output of this, let me copy this, and the output of this, if you will be able to see, and the output of this is exactly the same. Why is that so? Because we are using anyhow the same coefficients, same intercepts. It's just that I have saved that values in somewhere, some file itself, and directly I'm using that without doing the training part. So at each and every time, whenever you will load this pickle file, you will be able to get the similar data, similar output, I would say, because the coefficients are same, the intercept is same, right? So I hope that now it is pretty much clear to everyone that how basically we will be able to save the model, and then after saving the model, how we will be able to load the file and use it for uh, future test data predictions. I hope now it is very easy to understand. And with this, I think we are good to go for this session. I believe this is the only task which I want to show. Remaining things I have already conveyed. So with this, let's end today's video. I'll see you all very soon in the upcoming videos, where we will discuss further interesting concepts of machine learning. So now I hope that you have thoroughly enjoyed the complete life cycle of our project, where we started with understanding of the data. Then afterwards, if you will be able to observe, we have seen that how we will be able to prepare the data, considering that we have been provided sklearn bunch kind of a data set, and we have to convert it firstly into data frame, and then combining that target value with the independent features that we have, right? After that, we have had a great discussion about EDA, how we can do a model training, how we can do the evaluation of that model, how we can do the prediction, how we will be able to save that model, so that we don't need to retrain it again and again. All these things I have shown you practically with the real time data set, and I hope that you will be able to get an idea that how we usually do the implementation, how practically EDA is very important to get the best results out of it. What are the evaluation metrics that we have for the regression purpose? And with this, our complete module of linear regression is done, where we have talked thoroughly about the mathematical intuition. Plus, we have also had a great talk about the implementation for the same. In the upcoming part of the module, you will see that we will be talking about the bias versus variance trade-off, where we will see that the model that we have saw, linear regression model, it's okay, it's quite simple to understand, it's quite simple to have understanding of the mathematical intuition as well, but there exists a problem of overfitting, there exists a problem of bias versus variance trade-off, and that's where the concept of regularization techniques in linear regression came into picture. What are the algorithms in linear regression that we have in order to deal with that problem of bias and the variance? All these things we will talk about in the upcoming session of the module. So please stay tuned, and I hope that you have enjoyed this complete life cycle of the project also. And with this, bye bye everyone. I'll see you all very soon in the upcoming sessions, where now we will deal with the further concepts in machine learning. Bye bye everyone, and see ya.